All right, so we're going to take a closer look at an example that really kind of deals with some real examples from Power. So what we're looking at here, this is an example circuit. The circuit came from problem 9.6 in your textbook, but I've kind of expanded it to ask the set of questions that's shown over here. Okay. So what I wanted to be able to do is really kind of explore a lot of the concepts in single phase power and do so by asking a lot of different questions. All right, so this is the circuit that I've got over here on the left, and I want to go through all of these questions, and I'll kind of begin by saying, all right, let's figure out the average power supplied by this current source, and let's figure out the reactive power supplied by this current source, and then let's figure out the power factor and the instantaneous power and all of those sorts of things. Okay? All right, so we'll start with the average power. I want to get the average power supplied by this source. Um, to do that, I have to figure out really what's the voltage across that source, right? Now, first question we need to ask ourselves is basically this value right here, is this peak or RMS? In this case, I'm going to tell you that this is peak current. Okay. In other words, the current itself, I of t, must be 6 cosine omega t plus 45 degrees. All right, that's what I'm telling you in this case. All right, we need to be careful about that because if I have a peak value, I need to be careful about what I do with all my different expressions. Okay, all right. So to start, all right, basically I want to find the average power and the reactive power supplied by that current source. Simplest way to do that is basically to say, um, what's the complex power supplied by that thing? So really what I want to do is I want to figure out what is the voltage phasor across that current source. Okay? All right, so to do that, the simplest way of going about that is to say, okay, here's I. That I sees some total impedance Z. And I want to figure out what V is. Okay? So basically what I need to do is basically see all of this circuit and see that I have essentially a 4 ohm resistor in parallel with this capacitor, in parallel with this inductor, and this combination. In other words, I can say that that Z must be 1 over 4 plus 1 over negative 2j plus 1 over j plus 1 over 2 minus 2j. Right, where basically I've gone from right to left, sort of. So I've got these components first, then this component, and then this series right here. All right, that's my Z relationship. So over here you can see that basically I've put that into Matlab. Okay, this is example Matlab code. This gives you my Z equivalent. Now notice that I've put I in sort of phasor notation here. So this I is basically 6, so I put it as I equals 6 e to the j 45 degrees. Now notice what I've done. I have this pi times 180. That converts the 45 degrees into radians. Okay, and MATLAB does everything in radians. Okay, so I can figure out V pretty easily just by saying V equals I times Z. Okay, so what I'm going to do then, all right, what I'm going to do is I'm going to take this code, bring this over into MATLAB. All right, so I've computed Z. I know what I is. So Now I'm going to compute my V, and I want to see what the magnitude and the angle are. All right, so the first term here, the absolute value of V is the magnitude. I take the angle of V, I multiply it by 180 over pi to get the angle, and I can write over here that this must be 10.7331 e to the j 71.5651 degrees, or as we sometimes write that, 10.7331 angle 71.5651 degrees. Okay? All right, now, why do I want that? Well, I want to know the average power supplied by the current source, the reactive power. One thing I can do is I can always use the complex power. Okay? We know that complex power is equal to, complex power is always written like so. S equals P plus JQ. And I can write that as VI conjugate. And you got to remember about this. Given the fact that I've done everything in terms of peak values here rather than RMS, I have to multiply this by a half. I would not have to do that if I had RMS values, okay? All right, so I run through that calculation. Turns out that's also in my code here. So I will run that. Okay, and I see my S load. So what did I do? Let's take a quick look at my code. I said V times the conjugate of I times 0.5. So in Matlab, conjugate, all right, is like so, right? CONJ. And you can see that real quick. If I do I, you see here's what I is. If I write conjugate of I, you see that it's got the negative sign on the imaginary part. Okay? All right, so from this, what I've defined as S load, I see is apparently 28.8 plus J times 14.4. All right, now in terms of my power triangle idea, okay, I can say I've got P here, which is 28.8. And then apparently I have a Q that's half of that. So this is my Q equal to 28.8. Oh, sorry, not 28.8, half of that, 14.4. And my S value goes that way. So this is my S value, or what we call the apparent power. This guy here is, so phi, this is my power factor angle. All right, this guy is also, remember, angle V minus angle I, or the angle of the impedance. Okay, this is what we call sort of the power triangle. All right, and I can see from this expression, I've answered two of my questions. Apparently, this guy here is the power. This guy here is the reactive power. So what I say is my P is 28.8 watts. This is my average power. And my Q, my reactive power, is apparently 14.4 VARs. Okay, so this is my reactive power. Okay. All right, now a couple of things to note about this. The way that I have written this, all right, in the sense of, okay, I have a current I flowing into a voltage. This is really what I would think of as the load power, okay? In other words, these are positive, which is to say the fact that both of these are positive means the load is absorbing, okay? If I was thinking about the source itself, right? The source is apparently delivering 28 watts and 14.4 VARs. But if I looked at it from the source perspective, right? S source, technically I would have to say negative 28.8 watts and negative 14.4 VARs, right? So that S total equals S source plus S load. Just so we're clear, the source is negative 28.8 minus 14.4 J. The load is the opposite of that. You add those up and you get 0, which is to say energy is conserved across the circuit. All right, whatever power I source from this source is equal to the power I absorb in this load. All right, just to think about this real quick, just from the constituent relations and the passive sign convention. On the load side here, whenever I have current flowing into a plus sign, I say it's absorbing power. So power is written as basically, well, S is written as IV conjugate like that. When I have it over here on a source, it would be negative IV, well, negative I conjugate, not IV conjugate, sorry. I wrote that wrong. Right. This guy, when I'm a load, I have S equal to VI conjugate. When I'm over here as a source, I write it as negative VI conjugate. This is just like we did in DC circuits, right? If I have a current leaving a plus node, I have power as negative. Whenever I have current leaving or entering a plus node, I write power as positive. Same thing is true in these AC circuits. Okay, so we've answered our first two questions. I know the average power and I know the reactive power. 28.8 watts is supplied to the load, and 14.4 VARs is supplied to the load. Okay, all right. Now we want to figure out the apparent power. Well, the apparent power is the magnitude of the complex power, all right? Which we've said is basically VRMS, IRMS, or we write it as the peak value of V times the peak value of I, all right, times 1/2, okay? So remember where that comes from, the fact that VRMS is the peak value of V divided by the square root of 2 and the peak value of I divided by the square root of 2. So these, just to be clear here, these are peak values. Okay? Those two expressions are completely equivalent. All right. So now, how do I compute this? I got a couple of ways, right? I can use this power triangle. Essentially, I could use Pythagorean theorem to figure this out, right? I know what V and I are, so I could do it that way as well, right? I can also say that, okay, I know what this vector is, so I can take its magnitude. So in this case, how have I done that? Let's see. I'll take the magnitude of that S load vector and see the apparent power is apparently, according to this, 32.6 0.1994 volt amps. Now just to check ourselves, what I'm going to do is I'm going to take the peak value of V, so abs of V times abs of I, those are the peak values, times 0.5. Get the same exact answer. And I can also say, let's take the abs of V divided by the square root of 2. Okay, that would be the RMS value. I do the same thing for the current. I get the same answer. Okay. All right. So I can see I get the same answer either way. So now I got the apparent power. Why do we talk about the apparent power? Part of the reason we talk about the apparent power is apparent power for a load or a source is essentially the max for a given voltage. It's the maximum amount of power, real power P, that could ever be absorbed by the load. Okay. If you think about the power factor relation, the power is always going to be S load times the cosine of the power factor angle. In other words, the actual power is only ever going to be less than the apparent power. Okay, and so that's part of the reason why it's useful. All right. Next question I want to figure out is, okay, what's the power factor of the combined load? All right, so what's the power factor here? Well, to get the power factor, what I need to do is I need to get the cosine of this angle right here. All right, so there's a couple of ways to do it. I can get it from this triangle. All right, I can get it straight from my P relationship. So there's a couple of ways to do it. All right, I'm going to look at it like this. I'm going to say P for my load is equal to the apparent power times the cosine of phi. Okay, so in this case, right, I could plug this into here, take the cosine of phi, and I'd be off to the races, right? Since I know that the power is 28.8 watts. Again, I've already got that in my Matlab code. So I'm going to calculate that guy. So notice what I do. I take power factor as the real of my S load. So S load was my complex power. So I'm taking the real part, that's P, and dividing by S, right? So I'm saying my power factor, which is the cosine of phi, is P load divided by the apparent power, like that. Okay, all I've done is just rearrange this relationship. When I do that and I solve, okay, I find that the power factor is 0.8944. Okay, 0.8944 is my power factor. There's no units on that power factor. Okay. Now, a couple of other questions about this. One thing I might want to know is I might want to know what phi is. In other words, what's the power factor angle? Okay. So power phi is what we call the power factor angle. Okay. So one thing I could just do is to say, well, that's the inverse cosine of the power factor. Okay. That's one way to do it. The other thing is, I know that this is also supposed to be the same as the angle of Z. It's also the same as the angle of the voltage minus the angle of the current, right? So a couple of ways to compute this. And again, my Matlab code computes it all three ways. All right, so let's do this. All right, now again, before I run this, notice that so the first one of these, I take the arc cosine, inverse cosine of the power factor, multiply by 180 over pi, because Matlab, again, is going to compute an angle in radians, and I want to convert that to degrees. I take the angle of the impedance. I also take the angle of the voltage minus the angle of the current. And in all three cases, right, I multiply, excuse me, by 180 over pi to make sure that my answer is in degrees. Should be the case that power factor angle 2, and power factor angle 3 are all the same. So I run that, and I see in each case I get 26.5651 degrees, okay, for all three of those. Okay, so apparently my power factor angle must be 26.5651 degrees. All right, so from that, one of the questions that I asked myself was, can I use that to define what the voltage and current look like, right? Up till now, what I've done is I've computed the phasor here, but I want to figure out the actual time domain signals, okay? Well, I can do that, okay? I know in this case that I of t must be 6 cosine omega t plus 45 degrees. Now v of t must be whatever the angle, so the abs of v, so apparently 10.7331, that's the amplitude of it, and the angle of it, and again, angle defaults to radians, so I got to convert this guy to degrees. So I get that the voltage here is plus 71.5651 degrees. Okay, so there's my V of t and my I of t. Okay, and if I look at this, I can see that 71.5651 degrees minus 45 degrees is going to be that 26 degrees. In other words, the power factor angle is the phase shift between the current and voltage. All right, now a couple of other questions. I'm going to plot those, right? If I want to talk about the instantaneous power, remember that P of t is equal to I of t times V of t. All right, this guy should equal the real power or average power plus what we called in class, can't spell it here, it's a double frequency term, right? So I'll write it as a 2 omega frequency term. In other words, a term that has twice the line frequency, okay? All right, so I'm going to plot this in a second, and I'm going to make the assumption that omega is 2 pi times 60 hertz, all right, or 377, not 375, 377 radians per second, all right? We haven't been told in this problem what the frequency is, so I'm just going to assume it to be 60 hertz. And the reason that's a reasonable assumption, is, of course, is that in power problems, usually you're talking about 60 hertz power, at least if we're talking about a building or something in the United States. Okay. Now, before I do the plotting, though, there's one other question. Does the combined load have a leading or lagging power factor? Okay. How do I determine that? Well, this was my load power right here. Okay. This was the complex power absorbed by the load. What I see is that I have a positive P and a positive Q. If I have a positive P, we've always said that when P is positive, and we said this back in network 1, right? When P is positive, we are absorbing power. We're a load. Same is true with Q. If I'm absorbing Q, right? If I'm absorbing Q, then it's the case that my load is absorbing power. Okay, it's absorbing reactive power. Because I have a positive P and a positive Q, right? We basically say, we look at things like this. Okay, I say I look at my Q one of two ways. I say if it's greater than 0, I am lagging because my load is inductive. Okay? If it's less than 0, I say that I'm leading or that I must be capacitive. Okay? Lagging essentially comes into play whenever I am absorbing Q, and in this case, sourcing Q. Okay? So what you see is that capacitors are essentially sources of Q, whereas inductors are absorbers of it. All right, now a couple of things. The fact that I say this is lagging, all right, the implication of this being lagging is that the load is apparently inductive, right? If that's the case, if my load is inductive, it should be the case that my Z, let's calculate my Z, all right, here's my Z. Apparently what I've said with this is that my Z, my total Z in this circuit is 1.6 plus J times 0.8. If we look at just this imaginary part here, sometimes we call the reactance of this thing, right? That particular value, whenever that's positive, remember J omega L is inductive loads, and negative J over omega C is a capacitive load. Whenever the imaginary part of my impedance is positive, I am an inductive type load. Whenever I have a negative imaginary part, I have a capacitive type load. Okay? And so there's a lot to understand here. There's a lot of little things going on, but I can see this a couple of different ways. Whenever my Q is positive, I must have an inductive load. Okay? And we say we have a lagging power factor. All right. So I can see in this, I've got two things now. The fact that my Q is positive has led me to think that I'm lagging. The fact that my Z looks inductive, right? In other words, I can say this is some kind of, in looking at this, I can say that this is some combination of an R and L in series, okay? If I had a negative imaginary part, I would know that it was some combination of an R and C in series, okay? All right, now, the use of the term lagging comes from the fact that the current lags the voltage. Okay. In this case, if my angle of Z, which we said previously was 26.561 degrees, okay, 26.5651 degrees means that angle V minus angle I is 26.51 degrees, or that angle I equals, the angle of V equals 26.5651 plus the angle of I, right? If I have to add to the angle of I, then what I say is V leads I, okay? All right, V leads I. The term lagging refers to whether the current leads or lags the voltage. So since I is lagging, I is always lagging if I have an inductor. All right, to see that, let's draw our phasor diagrams. All right, now in this case, what are our phasors? So back to our original phasors. We said our voltage was 10.7331 with an angle of 71.5651 degrees. And our current, all right, our current was 6 with an angle of 45 degrees. All right, so if I do this, come down here. All right, our abs of V and angle of V 180 over pi. All right, so I can say that the 71 degrees would be somewhere up here, and 45 degrees would be right in between. So this is I and this is V. Now what we say is that phasors always rotate counterclockwise as t goes to infinity, right? As time increases, these guys rotate, all right, which means that I is always chasing V, so it's lagging. That always happens when I have an inductive type load, right? I know I'm going really slow and really pedantically through this, but I'm doing that on purpose because I want to relate how all these things kind of come together, okay? If I look, the angle between these guys would also be that angle of Z, okay? All right, that's the angle between them, right? Because what we said is angle of Z is equal to angle of V minus angle of I. Anytime that angle is positive, V leads I, or I lags V, and I have an inductive type load. Essentially, the way I can look at this is anytime that the I is behind the current. In other words, the I has a smaller angle than the V does. I'm lagging. Whenever the I has an angle bigger than the angle of the voltage, then I is leading V, and I'm capacitive. Okay. All right. So in other words, we say that the power factor is lagging. Okay. Which is equivalent to saying that I have an RL load, which sometimes I usually will just say inductive load. In other words, my load has some inductance. Okay. All right. So at this point, I've answered a lot of my questions. I've determined the power factor, right? I've determined that I have a lagging power factor in my combined load, right? Now I want to determine the time domain expressions for V and I. Well, I actually already did that as well, right? Here they were. Here's I, here's V, and I said that my power is equal to I times V. That should be equal to whatever my average power is plus that double frequency term, okay? So what I did was I now, next question I asked myself was to plot this, all right? And here's my code that does that. I'm going to copy and paste this. All right, before I do this, let's look at what I did. Again, I said over here I wanted to make the assumption, pretty logical assumption, right? That this was meant for 60 hertz applications. All right, so my omega is 377. Okay, so here's what I said. I said, well, my period, if I have 60 hertz, my period is 1 over the frequency. All right, my frequency is 1 over the period. My omega is 2 pi f. I defined a time vector here. Right? So I said start at time 0, increment times in steps of 1 over 10,000. All right, in other words, take 1 second and divide it up into 10,000 pieces. If you look at this, that means my time step here is like is pretty tiny, right? It's on the order of what is that, like 100 microseconds, right? It's relatively short. And I said increase until I reach time 2 times t. Okay. Now what I've done now is I say, so in other words, when I say 2 times t, what this is going to do is this is going to generate for me a time vector over 2 periods, and it's going to be sampled. In other words, all the values in this time vector are going to be spaced at 1 over 10,000 seconds. Okay. So now I'm going to plot I. I'm going to plot V. Now notice how I wrote this. I took the abs of V, right? That was the magnitude of my phasor. And then I have this cosine, and I put the angle of V in here. Now notice in all of these things, I put this in radians, and I put this in radians, because again, Matlab's cosine and sine functions and all of that, all their trig functions, are assuming that I have radians. Okay, and then I have this subplot command, and I plot first the voltage, then I plot the current, and then here I want you to pay close attention to this, I dot star V. I talked about this previously, but when I have this I dot star, this is P of t, right? I'm trying to multiply I and V like I've shown here. The reason I have this dot multiply is because I want to take every element in I and multiply it by every element in V. Okay? In other words, I and V are two vectors that have identical lengths. And if I want to multiply each element in I by each element in V, I need to use this dot multiply. I talked about that before. Now the other thing that I'm trying to do is, so right now I have V times I conjugate times 0.5. What I'm trying to show here is both the instantaneous power with this I dot star V, and by also plotting the real of V times I conjugate times 0.5, this should be my average power. So what should happen is this average power should sit right smack in the middle of this I dot star V. Okay, so let me run this. All right, and here's the plot that's generated. Here's my voltage, here's my current, and here's my P of t. So first of all, let's compare this to what we expected. All right, so I said that I of t should have an amplitude of 6, and looks like it does. All right, I said this guy here should have an amplitude of 10.7331. Looks like he does, just about. I want to add a data tip here. Let's see. Create new data tip. Looks like yeah. There we go, 6 amps. Okay. And I said that the P of t should have a double frequency, right? In other words, if the current and voltage have a 60 hertz frequency, this should vary twice in every period. If you look carefully, the P of t, which is the blue here, does vary twice a period. Now, the fact that the load is delivering some Q means that my P of t should go negative. If you look carefully here, you can see that. This guy is effectively going a little bit below 0. In fact, we can kind of see that if I do this. Yep. So that guy goes below 0 and then goes back positive again. The fact that he spends some time below 0 effectively means that he's supplying some amount of, or he's a reactive type load. If I had a purely resistive load, P of t is never going to go below 0. Okay? And I want to bring that data tip back up here at the top. I'm going to use that in a second. Okay? Now, a couple of things with this. I said that my load has a lagging power factor, right? And we said with a lagging power factor, right, I lags V, right? So if I look at this, V begins a new cycle before I does, right? V peaks here, I doesn't peak until a little bit while later, right? That tells us that I lags V. Now what I should see is that the phase difference between V and I is equal to this 26.5651 degrees. Now the way I can do that, I'm going to move this guy over for a second. Okay. The way I can do that is I can take the time difference between these two. All right, so when the current reaches his peak is apparently 0.0146 seconds. So I say 0.0146 minus, so this guy reaches his peak at 0.0133. Okay, that's the time difference between the current and the voltage. I want to get the phase difference, right? So what I do is I take that time difference and I divide by a period. This tells me the percentage of a period by which the current lags the voltage, right? I know that each period has 360 degrees, so I take that percentage of a period and multiply by 360, right? In this case, I get 28.08 degrees. That's really, really close, given the fact that this is kind of an inaccurate way to make this measurement, right? That 28.08 degrees is pretty close, right? Now, we said that our power factor was actually 0.8944. Let's see how close my power factor is with this 28.08 degrees. If I take that, I say cosine of 28.08 degrees, and I got to multiply that by pi over 180 to get it into radians. 0.8944, 0.8823 are really, really close. Right? That should end up being less than a 1% error if I look at it carefully. Now, I also want to see, if I look at my S load, the real part of that was the average power. It should also be the case that the average of this waveform, the average of my P of T, is equal to that real power. The way I can take the average of this in Matlab is I take the mean, right? So I say the mean of V dot star I. That's taking the mean of that P of T vector. I get 28.772. Compare that to what we calculated using our VI conjugate. Compare 28.8 to 28.772. If you calculate the difference between those two, you actually find that the error is less than 0.1%. All right, so essentially it's just about equal. All right. Now, that answers most of our questions here. All right, the other question I have is, so we plotted the instantaneous power, we determined the time domain expressions. Now what I want to do is I want to determine the real and reactive power absorbed in each impedance, okay? And determine if it's leading or lagging in each impedance. All right, so to do that, we got to look back to our original circuit here. All right, now essentially what I got is a current divider. So if I want to do this right, I really need to figure out a couple of things. I need to figure out this current, which I call I4, this current here, which I call I2J, this one here, which I call IJ, and this one, which in my Matlab code I called I other. All right, the other current. All right, now the easiest way to get those is to use the current divider relationship. Now, using the current divider relationship, all right, this is important. If I have a situation where I have Z1 in parallel with Z2 in parallel with Z3, I might have a whole bunch of other stuff. And let's say I know the current going in here, and that same current ultimately comes back out. That's the situation I have here. My current divider relationship, if I want to figure out the current here, all right, in this branch, the way I do that is I say I1 is equal to the I phasor times whatever my Z total is. Z total. That Z total is the parallel equivalent impedance of all these things in parallel with each other. I take that and I divide by, in this case, Z1. Now, where does that come from? If you think about this, the voltage across here is equal to I times that Z total. Okay? If I take that voltage divided by the impedance of this branch, that tells me the current in that branch. All right, so I divide by Z1. Essentially what I did was I wrote code again to determine those values. All right, so here they are. So notice what I did for I4. I4 being the current in this 4 ohm resistor. What I did was I said, all right, take I times Z, which is V, divide by 4. For I2J, which is this guy here through this capacitor, I do the same thing. I times Z divided by negative 2J, right? I divided by the impedance. Same thing for IJ, same thing for this I other, right? I do those calculations, and let's look in particular first at the 2J, this current right here, okay? If I look at that component, here's the code I used, right? So basically what I'm saying is that S2J is equal to V times I conjugate 2J divided by 2. Again, since these are peak values here, I have to have the over 2, right? The other thing I can say is if I'm just looking at a branch like this, right, where all I have is a capacitive load, the other thing I can say is I can talk about the P and the Q. P is equal to, in this case, I can always write this as abs of I2J squared times the real part of negative 2J, and the Q is equal to I2J squared times the imaginary part of negative 2J. Now, negative 2J is the impedance of that branch. In other words, I can always write my power and reactive power relationships in terms of these things. Now, there is no real part to negative 2J, meaning because there is no resistance, there is no real part, this guy is equal to 0. In other words, there's no real power in a capacitor. And this guy here, my Q, right, if I calculate that, I've done that here. So let's look at S2J. I have V times I2J conjugate, okay, times 0.5. That's this, okay. I've also calculated my Q value here by taking the current, taking its magnitude, and then multiplying by the imaginary part of the impedance. Now notice what I've done, right? Notice what I've done. I got to be careful, I guess, here in what I did, right? Because this is peak values again, because this is peak, I divide by 2. In both of these expressions, I divide by 2, okay? Or I use the RMS value. In this case, notice what I've done. I've used the RMS, right? I take abs of I 2J, and I divide by the square root of 2. So let's real quick run both of those expressions, okay? Notice what I get. I get that the complex power is 0 minus 28.8J, okay? P is 0 just like I predicted, right? Because this particular branch here, this particular branch has no real part to its impedance, has no resistance, right? In both relationships, both the VI conjugate approach and the abs of I squared times the imaginary part of the impedance give me the same result, okay? Now, what I have here in the remainder of my code was I did this for the other branches in the network, and then I added their complex powers up, okay? So this is in the 2J capacitor, this is the 4 ohm resistor, this is the 1J inductor, and this is that S other, which is in the 2 ohm plus the 2J capacitor branch. I add those up, that's what I get. If I look at S load, which I calculated previously, they're exactly the same thing, all right, which is what they should be. All right, so this is a long example and kind of slow in a couple of parts, but I think the important thing is that this really kind of takes you through how to analyze a lot of the important questions with respect to power and how power is calculated. Right? There's a lot of little details to it, And so hopefully this example kind of helps to understand some of those.